This is the VTech KidiGo walkie-talkie for ages 4 to 10. It may look like a cheap toy for kids, because it is, but there is one interesting thing about it. Not only does it claim to be safe and secure, which I guess could mean a lot of things, but the box actually says it has encrypted digital... Oop, the backlight turned off. The box actually says it has encrypted digital communication. Nowhere in the manual does it explain how it's encrypted or like what encryption standard it uses, but I did find this quote from VTech where they say it uses the industry standard AES encryption to communicate. I'm going to open it up and hopefully reverse engineer it enough that we can figure out if it really is encrypted. But first, I should just show you how it works. But this thing is so reflective that it's very annoying to film, so I'm going to turn the lights off really quick. Hold on. It is backlit, which is nice, because if it was reflective, it would have been really annoying to film. So it has three main options. The middle is sort of normal walkie-talkie, like push-to-talk mode, so you just hold the left side and then it talks. But it can also send these little animated messages. They play a little animation on the other side. And there are actually these little games like puzzle flipping and memory games. I actually haven't asked a 4 to 10-year-old, but I'm sure for that demographic, they're riveting. And then at the end, there's this wrench icon, and that brings you into the pairing. I feel like it's a little weird that they just threw this in the game menu because like your 4-year-old could just go here and press it and get confused, but whatever. There we go. It obviously has the battery indicator, and this is the signal indicator, but it's a cell tower. I guess they just took the metaphor from like a cell phone signal icon. Gotta teach them early, I guess. But there's obviously no cell tower because it's a walkie-talkie, so that's kind of funny. Anyway, that's basically what it does. So, now you might be wondering, this thing comes in a pack of 2, right? Where's the other one? Well, I kind of destroyed the case while opening it. I doubt anyone else is following along at home with their own, but the first part of the disassembly is not so hard. You just get rid of these 4 screws on the back. But guess what? There's a hidden screw underneath this front plastic layer, so you have to peel it up and then get that out of there. But I didn't know that. I mean, there's no iFixit guide for this thing, although if I was writing one, I would give it a bad score because of the hidden screw. But I didn't know it, so I just broke it off, and now it's sort of got a chunk out of it. But the inside still worked perfectly. And on the plus side, I've now created the thinnest and lightest KidiGo yet, which I think is pretty cool. So first we'll need this battery pack, which just takes 3 AAAs. And if we stick 3 genuine Sonys in it, and then connect it to the orange and gray wire, and then take this speaker and connect it to the green and purple wire. And it doesn't matter which way you put it. I don't even know why they put a red and a black side on it because, I mean, it's AC. It doesn't really matter, you'd think. But then if we turn this on and then press this, it comes to life. I imagine this is just like what Victor Frankenstein felt like. And just to prove it, I'll turn this one on. So I'll walk to the other room with this one and you should still be able to hear me.
It still works. It'll probably get you stopped at the TSA, but it works.
So I have a plan with this, with all these wires, and it's going to involve this microcontroller. And if you're wondering why it's still on the breadboard, it's because I can't get it out. I replaced all the retaining clips on this breadboard because it wasn't making good connections, but I think now it might be too tight. You just can't get it out of there. Anyways, I have a plan with this stuff, and it's going to be really cool. But first, let me do a tour of all the little chips on the board. Some people would use like a microscope or something, but I don't have that. So I have a better plan. I have this iPhone 5S, and I'm going to attach this macro lens to it, which should give us a really good view of the board. There we go. That's good. I guess I'll go from least to most interesting. We'll start on the front. This here, these capacitors and this regulator or transistor or something, I think this is all power circuitry. Actually, we can check. Hold on. So orange is the positive side of the batteries. And that, I think, yep, that is continuity right there with that side of that capacitor. And the gray side, which is the battery ground, has continuity with that side of that capacitor. So that's what that is. This is where the backlight connects. This is kind of cool because they just used this cute little PCB with 2 LEDs on it, and then that slots in 90 degrees. and then get soldered onto here. And of course, these are the buttons, and if you follow the 24 gauge rainbow down to the board, you'll see where it connects. This here is the little electret microphone. I think they just DC bias these and then amplify the AC output, which is pretty cool. And then we get to these two blob chips. Now this sucks because I think manufacturers just use these when they're so cheap that they don't even want to get a packaged IC. They actually just secure the die to the board and then put a bunch of gloop on it. And you can kind of see actually in like the shimmer of the epoxy there that like you can definitely tell there's a little rectangle in there and the little wires around it. You can see that it has all these lines going to the LCD. So this probably is or has an LCD controller in it. And then there's this one. And I don't know what this does. Maybe this is the like MCU that does everything. Maybe this is the brains of the operation and that one is just the LCD controller. Or maybe this is just flash. I'm tempted to say that like the bigger chip does more, but it might just be bigger on the board because of all the little wires coming out of it. So I don't know. And on the topic of the LCD, you'll notice there's the LCD ribbon under there. And that brings me to the work that I've done to secure this thing in place. So the LCD is secured with this very fragile paper thin ribbon. I think in the factory they secure these with something called anisotropic conductive film. So I really don't want to break it. I actually already tore it slightly, but thankfully I was able to solder it back. So I came up with this, frankly, ingenious solution, which is this cardboard and bread bag tie approach to keep everything secure. So I think it works pretty well, and it is covering up the ribbon a little bit, but there's nothing interesting under there. Don't worry, I'm not hiding anything from you. Now, back to the front, and this is the best part. So get excited. This is an EEPROM. This is an AT24C02A from Atmel, and I have the datasheet for it. It's a 2-wire serial EEPROM, and by 2-wire serial, they mean I2C. I don't know why, but I've read a few datasheets that for some reason won't refer to I2C as I2C, which if you don't know is just like a standard communication bus that has been in use for decades. They call it like 2-wire serial, but they mean it's I2C. And as you can see, this version, which is the 24C02A, only has 2,048 bits, or 256 bytes. So this thing is tiny. And that's definitely not enough for the software for this thing. There's no way. So there must be some other storage somewhere, which is why I think that might be flash. I don't know. So I don't know where that is because it's not the next chip, which I'll tell you about now. This whole area here, which is beautifully outlined in this, I'm sure, purely decorative silver rectangle, is like the RF section. So this is our antenna. It's labeled ANT1, but if ANT1 is so good, why isn't there an ANT2? This is the crystal. This is the 16 megahertz crystal oscillator, and I think it's just for this guy. The other chip probably has its own clock. I don't know where it is because there's no pins on those ICs. It's just a glop. But then we get to this star of the show. Let me see if I can show you the text. It's a little hard to see. This is the A7137, and I have a data sheet for this one too. It's from Amicom, I think that's how you say it, and it's a 2.4 gigahertz frequency shift keying transceiver. See, it says low-cost ISM band wireless transceiver. So that explains what's doing the actual transmitting. And you'll see here, it says it has a built-in AES-128 coprocessor. So it's looking good for the encryption so far. I mean, if there is encryption going on, this would be what's doing the AES on hardware and doing the transmission, obviously. You can see it communicates over SPI. So that's how it communicates with the main chip. And here's the block diagram. Super interesting stuff going on, like a fractional NPLL and a Gaussian filter, and a sigma delta modulator, which all makes lots of sense to me. I understand all of it. Totally. But there's one really interesting thing about this chip that I needed to show you. On page 80, section 21 of the datasheet for this thing, it describes the AES-128 security packet feature. And I'm just going to read you this because when I read this, I went crazy. So, A7137 has a built-in AES-128 coprocessor to generate a security packet by a general-purpose MCU. In addition to support 128 bits key length, AES-128, A7137 also support a proprietary 32 bits key length called AES-32. Now, I am no cryptographer, but I don't think AES-32 is NIST certified cryptography. And the numbers after AES, when you say AES 128, AES 256, what that number means is the key length in bits. So 128 bits or 16 bytes key length is considered secure, but, and this is against brute force attack, so just trying random keys until they work, which is like the most naive kind of attack. Every time you subtract one, you have the average amount of time for an attack. Basically, it's half as secure every time you remove a bit. So a theoretical AES 127 would be half as good as 128, 126 would be a fourth as good, and then 125 would be an eighth as good. Which implies that AES 32, which again is their proprietary thing, would be 1 over 2 to the 96 as good as AES 128 against brute force attacks. This raises alarm bells, because if this is what they're using, then I think, and by the way, I'm obviously not a cryptography expert. I hope you're not getting some advice on security from some random 16-year-old on the internet. What I think is that if they are using this AES 32, then that's like toy encryption. Like that should be very easily breakable without even doing an advanced attack, just brute forcing keys. So the big question now is, are they using AES 128 or AES 32? And I'm going crazy because I tried to look up AES 32 to see if there's any precedent for it, but I think it really must be their proprietary thing, because you like find like articles about implementations of AES 128 that use 32-bit like window sizes, but 32 bits key length is, I mean, that's like a joke. Like that's nothing, I think. So that's concerning. What I want to do next is figure out what's being sent between this EEPROM and the MCU, so see what it's reading and writing. And I hope that gives us some insight into the length of the keys, because if it looks like there's 4-byte keys in that EEPROM, then we'll know that it's AES 32. If we see 16 bytes of, random data, then it probably is using AES 128. So let's do that. I've changed the lights from VTech blue to red because we're getting serious now. The blood red symbolizes our fallen VTech KidiGo outer shell. Oh, and before I start doing this, I should say, if you're thinking, why don't I just look at this frequency area with an SDR, which is a software-defined radio, to just see what it's doing, and I could maybe even decode the FSK from that A7137 chip? Well, I do actually have an SDR. It's this thing, which I'm sure is not a very good one, but it cannot get up to the frequencies this thing runs at, which is, of course, 2.4 gigahertz, like Bluetooth and Wi-Fi. So, I'm going to work with what I have. The first step is going to be to power this thing from the Pico directly. What I'm going to do is I'm going to skip the battery and plug in straight to the VCC and ground lines of it, which I've, of course, soldered to and glued. I'm going to connect the 3.3 volts from the Pico directly to the 3.3 volt line here, which is scary because the battery line is regulated, obviously, but the 3.3 volt line obviously is not. So if I plug this into 5 volts by accident, I think I would probably blow everything up. And on the Pico, that looks like it's the 5th pin down, so 5 here. And then ground is going to be the 3rd one. Here, we'll plug in the speaker too, just to get the whole show running. You're actually not supposed to plug in these connectors to the other ones. It's like the wrong pitch. The other one is the right pitch. It's 2.54. It's the 0.1 inch pitch, but this one is really not for this, but it works. Okay, so now when I plug this in, and by the way, it's very stupid that I chose these pin instead of the socket style connectors here, because at any moment, if this shorts, it'll probably break stuff. So I gotta be really careful. But now I should be able to just turn this on. Yep, no battery connected, just from the Pico's 3.3 volt supply. So that's great. It does show this low battery indicator. I mean, it makes sense because whatever the ADC is seeing that detects the battery voltage is going to be, I would say 0, but I think their circuit actually puts the 3.3 volts back out onto the battery lines. Actually, let's see. So yeah, this is going to be here, our 3.3 volts. And then between these wires, the orange and the gray one, we're gonna see, yeah, also 3.3 volts. So it just goes right back through to the battery terminal. So this thing is probably reading 3.3 volts, which would be 1.1 volt per AAA. See, I can divide by 3, because that's gonna be the pretty low battery, because the right voltage would be 4.5 volts or 1.5 per cell. Then what I'm gonna do is hold down this, plug it back in, and this is what you use to upload the firmware to the Pico. And then I'm going to upload the software, which I'll link in the description, but it's basically an open source I2C sniffer for the Pico, which is super awesome. And now if I connect it, I gotta check the docs for that to see how you connect it, because it's not the normal way you connect it. Because usually you connect the I2C device to one of the I2C peripherals, but we're not on host duty. We have to monitor it, and this thing uses different pins. So 1 is SDA, which is I have is blue, and 5 is SCL, which I have is yellow. SDA is the data, and SCL is the clock. DA for data, CL for clock. And now, what I'm gonna do is, on the computer, which is gonna be picocom, unrelated to the Pico name of the microcontroller completely, /dev/tty.usb, modem, whatever it is, I always just do tab. And then it's gonna be that baud rate, 115 kilobits per second. And then, with any luck, once I turn this on, because I think it reads from it on startup, we should see the traffic read out right on the display. Ready? Check it out. There it is. 3 lines. And every time I turn it on, yeah, it's reading the same thing. Yeah, awesome. That's so cool. That is so cool. And now I'm curious. I tested it and nothing else reads. And as you can see, when I run games and stuff, like if I go here to send a game or whatever, like that's not sending anything across. But I'm curious, if I try to pair these two again, oh, see, that does write to it. Let me try that again. Let me just do it a couple times. Yeah, every time it writes to it. Okay, so now I have the traffic. So I'm gonna quickly analyze it and then I'll make some guesses about what it means. So. Okay, I think I cracked it. And okay, I'm not a child just because I like playing with toys for 4 to 10-year-olds and coloring. So I think with this and this, we can figure out what's going on. So these are all sort of meta, like they tell you what's going on, and then these are all bytes. Green is start, blue or A is acknowledgement, the yellow N is non-acknowledgement, and P is stop. So N tells it to stop sending bytes, and P is the actual stop event. So the first thing across the bus is this A0. Now, this is going to be the address of the device that's being communicated to. And I2C is not like point to point. I2C can have many devices on the same interface, all connected up to the same wires in parallel. So it needs to send the address with every transaction so it knows what it's talking to. But this thing only has one device, so it's just going to always use the same address. And it says here that the addressing for this device is going to be 1010, and then these 3 pins that are on the device. So if you wanted to put 7 or 8 rather of these in the same bus, could by just putting the pins low and high, and that'll give you a bunch of different addresses. But these are all 0 for this thing, so this is going to be 10100000, and then this bit is read write, so it's actually high or 1 for read and 0 for write. Sure enough, 10100000 is A0 in hexadecimal, so that's the address. So it's writing to A0, and it writes 1 byte, which is 70, and then starts again, and then reads from it, because now that bit is high, and then we read these 8 bytes. It's these bytes here, 75A, all the way to the end. Then we stop, and then everything stops. And that here is called a random read. So I've sort of compared it here. You can sort of map this to this. We send a start here. We send the address, which is A0. Then we get an acknowledgement, which is that A. Then we send the word address, so the offset, which only needs to be 1 byte because FF is 255, and this thing only has that many bytes, right? And then start again here in read mode, so that bit is now going to be high, A1, and then we read 8 bytes, and then when we send a non-acknowledgement, which I don't know why I did that. I did that the wrong color. That should be yellow. But when we send this non-acknowledgement, then it'll stop. So basically we read 16 bytes from 70 to 7F, and then we read the same 8 bytes again from 78, which, I don't know, I guess it's a bug, so I don't think this thing has over-the-air software updates, so I don't know if we're going to get a fix for that. Then we have pairings. So this, as you can see, looks a little different. It doesn't have this repeated start. And this is called a byte write. So we send a start, then we send the address, and then it's write, so it's low, so we get A0. Then we send the word address, or in other words, the offset, so 70, same offset as before, but we're writing instead of reading. And then we just start sending data and then stop. And you can see there's no non-acknowledgement here because we're not getting data back from it. We're writing to it. So we're in control. We can send a stop. We don't need to tell it to stop. So basically, this here, these 8 bytes are the data. So every time it pairs, because these are all separate pairing events, it writes these 8 bytes to offset 70. And, well, this might be bad news because as you can see, the random looking bytes are these, really only these 2. These are the only bytes that change between it. Then these bytes all stay almost the same. This one goes from 80 to 81. So 1 bit changes here. So in total, we're getting like 17 bits of change between each pairing, which if this is key transfer, and I think it must be because if you can buy a separate single unit of these, which they don't sell to you, but if you go buy one and pair it, if you can pair it with one of yours, then it must be transmitting the key because otherwise there would be no way for the key to be sent across. I don't think they're like permanently paired to the factory. So this must be the key transfer, but this is only 8 bytes. So if this is the key transfer, well, first of all, pretty bad key, it seems like. But second of all, that's only 64 bits. And well, it almost seems like this is the key here to me. So if that really is the key just right there, then they probably are using this AES32 with the 32-bit key length, and these are the 32 bits. Or these, I don't know what the specific offset is, but probably these. It'd be the most entropy if it was these, so we hope it's these and not these. But hey, VTech, that's not the industry standard AES encryption, that's... Shoot, I dropped my screwdriver. That's the proprietary 32 bits key length. So, that's not good news. So, the last thing I want to do is I want to read the entire EEPROM, just start to finish. So I'm going to quickly write a Python script to this, and then I'll just read the entire EEPROM and then print it out on screen. And then we'll read that from the serial console, and then I'll see the entire contents of it. So, hold down boot select, plug it back in. And I don't want to turn this on this time because I want to talk to the chip, but I don't want the MCU interfering. So I'll make sure that this stays off. So now I've written Python to this. I put the script on it. So now we'll go back to the terminal and run. Same as before. And then Control D. Oh, I forgot that I got to change the wiring because I'm reading it the normal way now and not the other way. So I'm actually going to use the I2C peripheral. So this is SDA and this is SCL. So that's going to be yellow on 2 and blue on 1. And then Control D. And there it is. There's the EEPROM. So you can see I2C devices, and then it says 50. 50 shifted 1 bit to the left is A0. In Python, we're looking at it as a 7-bit address instead of an 8-bit address because the read and the write are considered the same device. And then we have all of the beautiful 256 bytes. So let me quickly write that to a file as bytes, and then we can do a hex dump on it. Okay, so I've written the EEPROM data to eeprom.bin, and now if I run hexdump -c eeprom.bin, and no, I did not have the -c memorized. I checked the man page. So there it is. That's all the data on the EEPROM, and you can see it's mostly empty. At offset 0, we have some stuff, and then once you get to offset 2F, or even like 2.8, 2A, it's all null until offset 70, which was, of course, where all this stuff happens. And then there's nothing at 80 all the way until you get to like E0. And the little asterisk just means there's only no bytes there, so it just shortened it for us. And then on E0 to FF, we have some other crap, but that's it. So there's the EEPROM. And as you can see, those 4 bytes, which were written to it last time in the last pairing, 129B, 7C, FF, 81, those are right where they said they would be at 70. And well, we know that it only reads from 70 to 7F, and it only writes from 70 to 78. So my theory now is that I think maybe 70, 71, 72, 73 are 32-bit key, and then this is like the ID of the other device or something like that. And then maybe 78 is our key, and then 4 more bytes, which are like an ID of some kind. But it's interesting because if what we're getting is their key, then is our key not changing because we're not writing a new key, but we're getting a new key from them each time? I'm not sure. So we don't know what's going on with that. But what I do know is that I think that's enough reverse engineering for now. I guess the next step is to open the other one. I hope correctly this time, hopefully, and dump its EEPROM and see what it's sending. And then I guess maybe eventually use an SDR or something. I guess I'd have to buy that. I don't know if anyone's gonna care about this, but if anyone does, then hopefully I can make another part where we dive more in depth. And also, I'll link everything else in the description. All of this stuff, all these data sheets, I'll put all the info down there. And if anyone else opens one of these up and looks at it, maybe someone else with an SDR can figure out what's going on there. First of all, open it properly. Then absolutely comment that, and you can email me, because if anyone else has any information, I would love to hear it. Anyways, thank you for watching, and goodbye!